All right, statistics students, so I want to take you through the other major case study in chapter 11. This is the blood barrier problem, and the first case study we talked about, the one with the alcoholics and the non-alcoholics and the enzyme in the stomach and the men and the women, that one was really focused on looking for outliers and what to do with the outliers. This one is much more about model refinement and how to figure out how to make the best model. And this is important in several of your homework problems, so you definitely need to know how to do it. And sometimes there are problems that have both model refinement and outlier situations, so you should be able to combine the methods learned in both of these. So we're going to start with the chapter 11 PowerPoint, and we're starting on slide 23. So this problem is about how when the blood is brought into the brain, there's this layer of cells that makes it so that big stuff can't get from the blood straight into the brain. And this is really useful because it protects your brain from like random junk in your blood that might be poisonous or hurt your brain. Brains are really important. We want to keep them. The big problem with this is if you have a brain tumor and you try and treat it with a drug, it can't get through that blood-brain barrier, and so it can't treat the tumor. So the experiment at hand was trying to figure out if you give this like medication to try to break the blood-brain barrier at least a little bit, make it a little bit more permeable by adding like a sugar solution to the blood, would that make it so that anti-tumor medications would be more able to get into the brain and treat tumors in the brains? And that would be useful for treating like brain cancer. The problem is you need to compare that to somewhere that doesn't have a blood-brain barrier, like your stomach or your liver or some other part of you that's not your brain. So they use the liver as a control because the liver doesn't have a blood-brain barrier. So they're looking at this treatment. Can we apply like a regular, just like slightly salty water versus this glucose treatment, and will that affect how the medication that we're trying to give to get rid of tumors in the brain will get in and act on the tumor? And they're doing this on rats because it's like not cool to experiment on people. So that's what's going on. The response variable, you'll see this in your textbook on page 314. The response variable looks at the ratio between the antibodies in the brain tumor versus the antibodies in the liver, as a way of comparing how much made it through the blood-brain barrier versus how much just like made it into the body in general, and the liver's like a representative of the rest of the body. So let's go into slide 24. We're looking at the variables, and we have the brain and the liver. That ratio is the response variable. That's what you're interested in modeling. You have the time since the treatment, and you might expect that the effect of the treatment would increase over time since the treatment, so you want to take that into account. They've harvested or like killed the rats a certain amount of time, so half an hour, 3 hours, 24 hours, and 72 hours after they applied the treatment. And then the treatments are BD, that's the sugar solution. They're trying to break the blood-brain barrier with that, versus NS, which is just like the control. So those are the two variables that you really actually care about. Then you have this other variable. You have days since they were initially injected with the thing that made them have the tumors. That might matter. They're not really interested in it, but they couldn't inject the rats all on the same day, so they need to take that into account. They have the sex of the rats. They hope that doesn't really affect the outcome, but they need to take that into account. They have the weights of the rats. It's possible that like heavier rats are less affected, or lighter rats. They have how much weight the rats lost, and that it's possible that it could be related to the response, because it could be that like they lose more weight when their tumors are growing more in their brains. Similarly, the size of the brain tumor could also be related to the response, because if the antibodies and the drugs are working, then the tumor isn't growing as much, and the tumor wouldn't be as big. So these second two, they might make the experiment hard to interpret if they turn out to be significant. So to be really conservative about interpreting this new drug, the researchers want to make sure they take those potential things into account. So these last 5 columns are called covariates in the sense that they're things the researchers have to take into account that they didn't experimentally manipulate and they're like not really directly interested in. They just have to take them into account to be conservative and fair. All right, so we'll go to slide 25. The research question is, did the antibiotic concentration in the brain tumor increase when the blood-brain barrier was disrupted by the BD solution? Basically, did this treatment work? Okay, so we start by looking at the graphs, and if we go to slide 26, we're just looking at time since the treatment and that this ratio of the antibodies in the brain versus the ones in the liver. This is really bad. We look at this and we can see equal variance is going to be a disaster here. Like the low times have almost no variance and the high times have a tremendous variance. And so I can't go forward without considering some kind of transformation. So we can play with lots of different transformations, but it turns out that the log of both works pretty well in this case. Okay, so we did the log transform of both. We're going on to slide 27 and we're going to look at this matrix scatter plot. You guys did this on your last couple homeworks, but let's look more carefully at this one. So the top row is really the interesting row here. And you're looking at the log of the ratio of the brain versus the liver. And that's your vertical axis of this. The things you're most interested in are the time, because that's an experimentally manipulated variable. So you're looking at the graph up in the top right corner. It might be a linear relationship, but looks a lot better than it was before we did the log transform. This is definitely an improvement. If we look at the relationship, the second one from the right, the log ratio on the y-axis, the tumor size on the x-axis, we don't see any really strong trends in the green points, but maybe there's an increasing trend in the blue points suggesting, so the blue was the control. It looks like the tumor is bigger when the ratio is bigger. It looks like there's not a strong relationship between the ratio and weight loss. We can look at the relationship between the ratio and the actual weight of the rats. That looks like it might be a positive relationship. And then it looks like there might be a positive relationship between the log ratio and the days. None of these do we look at this point with the log transforms and say like, oh my gosh, these are totally nonlinear. We definitely need a transformation. So like we're pretty okay to proceed from here. So we'll go on to the most obvious model would be to model the log ratio with the treatment, the log time, the days, the sex, the weight, the loss, and the tumor. I'm not including the interactions to start with because that would make a super complicated model. And they didn't really ask about interactions, so I'm not going to make my life harder. So I can go and look at the partial residual plots. And remember, these plots are looking at the effect of one thing after accounting for all the other things. So if we go on to slide 29, we look at the partial residuals. Up in the left corner, it looks like the treatment probably does matter after you account for all these other things. It looks like the time is maybe not linear. I mean, we've fixed the variance problem, but you'll notice that the second treatment in particular is quite a lot lower than the line. And that kind of makes me uptight because I could think about time as a linear thing, or I could think about this as four groups of time. And this is making me think maybe I should treat time as 4 different categories instead of being linear. Let's see, I look at days and it's like really hard to tell what's going on with that. I look at the sex, there might be a difference there. It's not super obvious that there is one. It looks like there's not much of a difference with weight. It looks like there might be a difference in weight loss. Maybe the ratio declines as weight loss increases. And there might be a relationship between that ratio and the size of the tumor. So just looking at those makes me think probably the next step of model refinement is to do a better job of modeling time. And instead of thinking of time as linear, thinking of time as 4 groups. So that's going to be my next step. I'm going to do that in slide 30. And what you can see here is my linear model 2. I've changed my formula. Now instead of using time as numeric, I have factor time. So I have like factor and then time in parentheses. That means I'm treating time as 4 groups. And I want to use an extra sum of squares f-test to see whether this was the thing to do. So I do that on slide 31. My extra sum of squares f-test, my p-value is 0.03. That means there's strong evidence, or there's moderately strong evidence. 0.03 isn't a really small p-value, but there's moderately strong evidence that my more complicated model is better. And my more complicated model is thinking of time as 4 distinct categories rather than continuous. So that means I do need to model time as 4 distinct categories. So let's look at the partial residual plots. If we do that, instead of modeling time with a line, that middle top graph, which earlier was a line, now is a box plot. That's cool. That's what we were aiming for. Now we really have less evidence that days, sex, or weight matters. It looks like maybe once you properly model time, those are less of a big deal. It's unclear whether loss or tumor matters still, based on looking at the partial residuals. So these partial residuals were particularly useful for figuring out that time was not best modeled linearly, it was best modeled as 4 categories. All right, so now we look at our model. That's on slide 33. This is the model with all the things in it. And if you look at this, one thing you notice is like a lot of these things are not significant. And a way of refining models is called backwards elimination. And the strategy here is 1 by 1, you get rid of the least significant thing. So if we look here, the least significant thing is days. It has a p-value of 0.95. So we're going to drop it from the model and see what happens next. So going to slide 34, we dropped it from the model. Cool, there's still a bunch of not significant things. So the next least significant thing is sex, and the p-value for that is 0.89. So we're going to drop that from the model, and we go on to slide 35. Still a bunch of non-significant things. Now weight is the least significant. It has a p-value of 0.769. So we're going to drop weight. We go on to slide 36. Still some non-significant things. Only thing that's not significant here, well, maybe there's 2 things. The one that's least significant here is the tumor. The p-value is 0.208. We're going to drop that. That takes us to slide 37. Now loss is non-significant. It's got a p-value of 0.16. We drop it. And we come to our final model. This is cool. It's cool that we could drop all of our covariates. All of the covariates were things we weren't really specifically interested in. We just felt like we had to model them to be thorough and cautious. So we come to our final model and we realize these are the things that we actually experimentally manipulated, and we're pretty happy with this model. So this is what we're going to use going forward. One thing that's annoying about this model is that the thing that's actually the treatment is called BS. And so R has considered that as like the control because that starts earlier in the alphabet than NS, which is actually the thing that's the control. I want to be able to say how much better than the control the drug works, not vice versa. So I need to switch how that's coded. So if we go to line 39, I've changed the coding. So I have this my treatment is a factor and I change the levels. So instead of considering BD the base case that's modeled, I'm considering NS the base case that's modeled because I know that's the control. And then I rerun the same exact model just with those coded slightly differently. So I go on to slide 40. That's the same model, but now this last line, this pink line, tells me what the effect of my treatment is. That's really cool because that's what I want to be able to do. All the blue lines are telling me about the effect at different times since treatment, and the intercept is telling me what the effect is at 0.5 hours, and then the intercept plus 1.13 would tell me what the effect is at 3 hours, and then the intercept plus 4.257 would tell me what the effect is at 24 hours, and so on. So that's how we would interpret. You could make an equation from this. It would be like a log ratio of brain antibodies to liver antibodies equals each of these factors, but remember they're on a log scale as well, and then plus the effect of the treatment. Okay, so we go on to slide 41, and this is where you actually interpret the coefficients. So remember, we were working on a log scale, so we need to exponentiate. So we can get the coefficients out of the model. This first line says beta gets my coefficients, and the fifth one is the one that's the effect of the treatment. I colored that pink in the slide. Now I need to exponentiate it, so I do e to the fifth one, and that is the estimated effect size of my treatment, this 2.21. And then I can get a confidence interval and exponentiate that, and I can get the lower and upper bounds of the confidence interval. So in the end, I can say the median antibody concentration in the tumor relative to the liver was estimated to be 2.22 times more for the rats with the barrier disrupting treatment compared with the control treatment, and my confidence interval for that is 1.52 to 3.22. You should be able to do this. You should be able to back transform when you have this log variable. Yeah, that's what they do in the book. Okay, there's a couple other little wrinkles here. So one thing is we didn't look at whether there was an interaction. Does the effect of the treatment depend on the time? Like maybe the treatment is more effective initially, but over time it's the same as the control. We would want to know that, and we didn't include that possibility in our model. So we need to rerun our model. So our first model is model 1 on this slide. On slide 42, it's time as a factor plus the treatment. And model 2 is time as a factor times the treatment, and that times means I'm interested in considering the interaction. And I'm going to do an extra sum of squares F test here. And what I do, when I do this, I get an ANOVA p-value of 0.9175. That means there's no evidence that I need the more complicated model, which means there's no evidence that I need an interaction, which means the effect of the drug doesn't depend on the time. Sweet. So I can say the effect of the blood-brain barrier drug does not appear to depend on time since treatment with a p-value of 0.92. Cool. All right, and then we have a last slide. I just wanted to show you this one. It's pretty. It's a nice way of presenting your results. If this was your homework, you might want to make a pretty slide like this. And what you can see is that there's a nonlinear relationship between the time and the effectiveness, but that it's pretty much the same difference between the two at all the treatments. So the solid line is about the same distance away from the dashed line at all the treatments. That's what we mean by saying there's not an interaction. And in general, the treatments are the green circles. They are indeed above, on average, the orange triangles. So that is the last example from this chapter that I'm going to walk through. Hopefully now you have a sense of what to do when you encounter outliers and how to start refining your models. We're going to use log transforms as we look at the scatter plots, and we need to think about whether we're going to add squared terms or whether we're going to convert variables that are quantitative to categorical variables, which is what we did here. Okay, bye.